We'll now do some additional examples of separable equations. And let's try. So that's the next example. I want to solve the following ODE. Xy prime is equal to y square plus 1. So the first question is this separable? And the answer is yes, because even though the right-hand side, we still have something on the left-hand side, and we need the equation to be in the normal form, right? Y prime equal to f of x times g of y, we can still rewrite this equation in that form. That would be one possibility, but I'm actually going to try to avoid writing this as f of x, y. I'm going to try to separate variables immediately because, again, just by looking at this equation, I can sort of guess that it will be separable. So I'm going to write y prime as dy over dx. So x dy over dx is y squared plus 1. And then clearly, I can divide both sides by x and by y squared plus 1 and multiply by dx to get dy over y squared plus 1 equal to dx over x. So, and that certainly is separable because different variables are on different sides. So then we can integrate. Integral of dy over y squared plus 1 is the same as the integral of dx over x. Then you should recall that the integral of 1 over y squared plus 1 is arctangent of y, and integral on the left is natural log of absolute value of x plus a constant. So that would be our family of implicit, one parameter family of implicit solutions. And then recall that also, let me finish writing this, of implicit solutions. Recall that besides the one parameter family, I needed to seek equilibrium solutions, which were all values of y, where this function is equal to 0. But clearly, y squared plus 1 is never equal to 0, so we can conclude that since y squared plus 1 is never 0, then we have no equilibrium solutions. Okay. All right, and in this case, actually, if I want to get an explicit solution, this is really easy to solve for y, because if I have arctangent of y, I'll recover y by taking tangent of both sides. So arctangent of tangent of y is y. Y is tangent of ln of absolute value of x plus c. Another example. Y prime. So I want to solve y prime is equal to xy plus y plus x plus 1. So at this point, the only type of equations that I know how to solve is separable equations. And separable equations have the right-hand side as a function of x times a function of y. Clearly, in this case, this is I'm adding four different terms, so it doesn't look like this is separable, but maybe I can manipulate to change this to a separable equation. So I'm going to manipulate the right-hand side of this equation. In what way? So I can collect common terms. There is a common factor of y in these two guys. So this should be y times x plus 1 plus, and these two I can also associate together, x plus 1. So then there is a common factor of x plus 1, and you get y plus 1 times x plus 1. And this is a separable of D. Okay, so then because it's separable, first we find equilibrium solutions. So how do we do that? We need to set y plus 1 to be 0, so y equal to minus 1 would be the only equilibrium solution that we got here. And then number two, separate variables and solve. So in this case, dy over dx is y plus 1 times x plus 1. So this is dy over y plus 1 is equal to x plus 1 dx. So variables have been separated, so now I can integrate. So integral of dy over y plus 1 is equal to integral of x plus 1 dx. Let's compute the x integral first. That's the same thing as an integral of x dx plus integral of dx, x squared over 2 plus x plus the constant. And now what about the second integral? I can use a substitution. U is y plus 1, so that du is dy. Then the integral becomes du over u, and it is equal to ln of absolute value of u. Again, notice I'm not adding the constant here because I already added it on the right-hand side. And now who is u? U is x plus 1, so this is ln absolute, value of y plus 1, because u is y plus 1. And so then what we got is an implicit solution, family of implicit solutions. Ln absolute value of y plus 1 must be equal to x squared over 2 plus x plus c. So my equilibrium solution in this family of solutions then form a set out of which I should be able to find all possible solutions of the equation. Another example. Let's say I want to solve dy dx. is equal to e to the power 3x plus 2y. Would this be a separable equation? Of course, yes, if we use properties of the exponential. What does it mean to have e to the 3x plus 2y? That's the same thing as e to the 3x times e to the 2y. So the equation is separable. Then number one, e to the 2y is never equal 0. So there are no equilibrium solutions. So we can try to separate variables. Divide both sides by e to the 2y and multiply both sides by dx. What we'll get is e to the minus e to the, let's see, e to the 3x dx. That is equal to e to the minus 2y dy. Right, so I moved all x's on the right to the right, and I move all y's to the left, and I just wrote things backwards. But equality works in either way, so it really doesn't matter. So then we integrate the integral of e to the 3x dx should be the same thing as the integral of e to the minus 2y dy, and so therefore 1/3 e to the 3x should be equal to minus 1/2 e to the 2y plus a constant. And that is again an implicit solution of the ODE. So to summarize these developments, basically what you see is that when I'm trying to solve a separable equation, really, I'm not doing anything that is too elaborate in terms of solving the equation. The only thing that I have to do is to recognize that the equation is separable and then separate variables and then integrate. And the only difficult part is a part with integration. And for that reason, I implore you to review integration as soon as possible. Let's do just one more example. Let's try to solve y natural log of x dx dy equal to y plus 1 over x squared. Would this be a separable equation or not? So let's investigate this. Well, first of all, if I have a square of a ratio, that's the same thing as a ratio of squares. So y plus 1 squared divided by x squared. And now I can try to separate variables. If I'm able to do it, then that means that the equation is separable. So we'll move all y's to the right and all x's to the left. And so what do we see? On the left, we'll have x squared ln of x dx. And then on the right, I'm going to have y plus 1 squared divided by y multiplied by dy. So this is a separable equation. Because I'm able to put x and y's on different sides. And so I will be able to solve this equation if I evaluate two integrals. One integral is of x squared ln of x dx. And then, of course, the second integral is integral of y plus 1 squared over y dy. Let's do the second integral first. So in this case, sort of the easy approach is going to be factor out the numerator and divide by y. So numerator is y squared plus 2y plus 1 divided by y dy. And this is an integral of y plus 2 plus 1 over y dy. And then this is rather simple because integral of y is y squared over 2. Integral of 2 is 2y, and integral of 1 over y is ln of absolute value of y. I'm not writing any c's because I'll put c with x. And then the second item that I need to compute is the integral of x squared ln of x dx. That is the left-hand side of the expression. And because of the presence of ln of x, that's a good indication that I should use integration by parts. If u is ln x, du is dx over x, and if dv is x squared dx, then v is x cubed over 3. So then my integral is going to be u times v, x cubed over 3 natural log of x, minus integral of v du, and that is x cubed over 3 times 1 over x squared over t. So the second integral we can evaluate to get x cubed over 3 natural log of x minus integrate, we get x cubed, integrate x squared, get x cubed over 3. There is already 1/3 in there, so minus x cubed to the 9 plus constant. And so now I need to bring both of these things together. Let's do this again. So integral on the right is equal to the integral on the left. So x cubed over 3 ln of x minus x cubed over 9 plus c must be equal to y squared over 2 plus 2y plus ln absolute value of y. Okay, so that is going to be an implicit one-parameter family of solutions. And is that it, or should we look for other solutions? So notice that in this case, I wrote a derivative dx dy. So I'm looking at x as a function of y. So if I want to find equilibrium solutions, I have to set, so to find possibly additional equilibrium solutions, what would I need to do? I need to put this equation into a normal form, solve for dy over dx. And what's it's going to be? So it will be still y plus 1 squared over x squared. And y of ln x go onto the right-hand side. So copy this. And this actually is dx over dy. So 1 over y ln x. So in this case, y is a independent variable, x is dependent variable. So I'm looking for values of x, and actually let's write this as a separated equation. So this is y plus 1 squared divided by y times 1 over x squared ln of x. So if I solve this as a function x of y, then I need to set 1 over x squared ln x to be 0. And 1 over x squared ln x is actually never going to be 0. So this guy is not never equal to 0. So then there is no equilibrium solution, where x is a function of y. All right, so then next time we might do a few more examples of separable equations, and then we'll move on to the next type of equations after that.